So you've got a couple different things going on here. First and foremost, we hear reference to solubility. What is solubility referencing? Okay, so it is going to reference forces, but how do you use those forces to decide if something is soluble or not soluble? So the use of the term polar and nonpolar, particularly those people that finished the lab report last Friday, for those people in the lab, hopefully they did not use the terms polar and nonpolar, and if you did, you should go back and change that because I have yet to go in and grade things. But using the terms polar and nonpolar is going to be a very dodgy thing to go through and use, particularly within the context of the lab. Define polar.
The difference in electronegativity between 105 and less than 107.
Cool. If we're going to reference the difference in electronegativity, okay, dropping to between 0 and 0.5, or sorry, we said polar, 0.5 and 1.7. That's referencing a chemical bond. When we talk about solubility, what's happening? When I dissolve sugar in water, have I lost water? No. So the chemical bond does not change when we dissolve things, which means referencing the terms polar and nonpolar with respect to the bonds is irrelevant because the bonds don't change when you dissolve something. Right? And that becomes one of the big problems, is that everybody's using these terms polar and nonpolar with respect to the bonds, and those are 100% irrelevant-ish when we talk about solubility. What dictates solubility is the forces. Okay, well, how are those forces used? I have a force, dipole, dipole. Does that mean I'm soluble? Okay, what is soluble in reference to? Saying forces is important. That is an important distinction. But how do I use that if all I know, a dipole, dipole, that's a force. Do I dissolve? Similar forces dissolve. That's a little bit better because now what we're referencing is that we need to look at two different things. We look at just the basic level for solubility and things dissolving. I already stated an example, taking sugar and dissolving it in water. Solubility is looking at two different substances and what happens when I mix them. If they mix to form a homogeneous system, they're now soluble. If they stay heterogeneous, they're insoluble. So it's comparing two different things. So when we're looking at solubility, yes, it's forces, but what we're talking about is like forces dissolve like forces. So in the system of I have dipole, dipole, does that mean I dissolve? Well, I've only defined one of them. It could mean I dissolve. It could also mean I don't, because I need to know what the other thing is. So solubility is always a comparison between two things. You have to make sure you understand what those two things are before you go into the question. Right? If you're looking at a question, more than likely, one of those two things is your answer choices. Where's the other thing? So we're looking at forces from compound A, and we're looking for forces from compound B. If we go through and say all of our answer choices are possible A's, what is B? Non-soluble is saying that I take these two things and they don't mix. So far, all we've defined is one thing. So referencing solubility isn't useful. I need to know what the second thing is. What is the second thing I'm comparing all of these A's to? Where was that found? In the question. You have to go back and pull the information out of the question. Solubility is really just asking you to look at one thing. You have to see the other thing given in the question, which means you have to be very careful about reading through that process. Okay? So back to our question, we're looking at polar aprotic solvents. One of the reasons why I don't like the reference of going to polar and non-polar as a reflex for these things is I will very commonly get people go, oh, I'm just going to Google what it means to be a polar solvent. That's great. Okay, you now know what it means to be a polar solvent. Is that what the question asked? No, it said polar aprotic. And if you just Google polar aprotic, maybe you're getting a polar aprotic definition. You might also be getting two definitions. What it means to be polar and what it means to be aprotic is two separate things. Those things need to be grouped and categorized together. That's the point of what the lecture videos went through and did, was to define what's happening within those systems. So if we're looking at a polar aprotic solvent, what does that mean?
With dipole-dipole force.
We're going to be generating a dipole-dipole force. The dipole-dipole force is coming from polar covalent bonds. Okay? That's the term polar, is in reference to our polar covalent bonds. Okay? So I accept that in our explanation of the word polar. You said weak. That could be a little bit hard to define. Okay, how are you defining weak? I know we're putting you on the spot. How are you defining your weak?
Will be non-hydrogen bonding.
Ah, there we go, which is perfectly acceptable. Acknowledging that we have multiple different forces and that hydrogen bonding is a specific example of dipole-dipole is phenomenal, and you're saying it's not hydrogen bonding. Okay? I would argue that's not weak. What is that? Your reference of not hydrogen bonding is phenomenal. I love it, but it has nothing to do with the weak dipole-dipole forces. What does it have to do with specifically? The aprotic statement. Okay? Whoops. Not H bonding is still a polar covalent bond, but really what that's defining is the aprotic aspect. Make sense?
Could you define aprotic?
Yeah. Not hydrogen bonding.
That's it?
Yeah, that's it.
Okay.
Okay. What aprotic is referring to, does anyone have an example of that? A means not as a prefix. Okay. So it's really just saying not protic. Well, what is protic in reference to?
Hydrogen bond, I'm assuming.
Sort of. I mean, yes. What things are prot? Think acids and bases. What things are prot? Protons. Okay, and if we were talking about acids and bases, when we reference proton, we're not referencing the subatomic particle. What are we referencing? I saw it. Where'd you look? Yeah? You're not looking at the whole thing. Where are you looking very specifically? At the top left. Okay, I accept that. So what are you looking at specifically? Top left of our periodic table is hydrogen. So when we're talking about protic, what this is very specifically referring to is the atom that only has one proton. The atom that only has one proton is hydrogen. So when we're talking about protic, what we're referencing is a hydrogen that is positively charged. How do you get a positively charged hydrogen? Back to your definition. It has to be bonded to something that is incredibly electronegative. You mean like nitrogen, oxygen, or fluorine? Yes. And if I have a hydrogen bonded to a nitrogen, oxygen, or fluorine, what have I done? Hydrogen bonding. So aprotic quite literally breaks down to not hydrogen bonding. That's it. Okay? So now what we're looking for is very soluble and polar aprotic solvents. Okay? We've defined what our force is. We're looking at just dipole-dipoles, and we're not looking at hydrogen bonding. So now we want to go through and look at all of our potential options to explain what things could potentially tie to that. This does become challenging when it deals with solubility, because when we look at our solubility forces, we've got ionic, hydrogen bonding, dipole-dipole, and our London dispersion forces. Just because we are looking at compound, we said B was blue, sitting here, okay, what things would be very soluble? Well, things that would match that force. So we could go through and look at these and say which of those match that force. If they match that force, that should be an answer. Does that make sense? Okay. Of the things that are shown up here, we really only see one. Okay. And how do I see it that fast? What am I looking for? Said another way, what am I not looking at to establish my dipole-dipole force? Hydrogens. Every single, well, almost all of those have hydrogens. So does that allow me to whittle any answers down? This could tell me it doesn't have hydrogen, so does that mean it's soluble or insoluble? It's a good question. I said I knew which one was dipole-dipole. So hydrogen's not helpful because hydrogen shows up everywhere. So I don't want to be looking for hydrogen. That's something that's immediately removed from my list of visibilities. How do I know I have a dipole-dipole force? And that becomes a challenging question. All of our forces are the interaction between two molecules. We will only ever see one molecule written out. So how do I know by looking at a molecule what its force is predicted to be? Where do I get a dipole-dipole force from? Where do I get a dipole-dipole force from? A polar covalent bond. How do I know I have a polar covalent bond? Say that again. Okay, so in that reference of hydrogen, what am I immediately doing? I'm looking at my answer choices and I see hydrogen bonded to carbon, deleted. Because that fits my nonpolar system. Deleted nonpolar system. Okay, those are now off my periphery for any kind of interpretation. Okay, I also want to ignore ionic. Deleted. Deleted. That one was trickier to delete. Why can I delete that one? Not good enough. Why can I delete that one?
It would be non-polar covalent for the nitrogen and chlorine.
This one's a little injury, perhaps a little salt to injury here. Ammonia is something that you should have picked up and learned and maybe been asked to have memorized and all the way back in fundamental chemistry, which meant it should have showed up in 151, which meant it should have showed up in 152, which means by the time it shows up here, you should know what's going on with that. Ammonium, NH4, is a cation bonded to the chloride as an anion, which means that interaction is ionic. I'm looking for dipole-dipole. So by looking and deleting all those carbons to hydrogens, I was getting rid of nonpolar covalent. But as you correctly said, Jazz, what we're looking at is everything that's not ionic or nonpolar covalent. So that middle one I should also eliminate from purview because that's ionic. Okay? So cool, we did a lot of elimination. I'm now just looking at two pieces. What's the next piece of information that I'm looking for? So we could push to hydrogen bonding. How do you get hydrogen bonding?
Bonded to nitrogen, oxygen, and chlorine.
So you've had enough of daddy's. Sorry. Thinking about talking to my kids. That was. Jimmy, can I delete that record? Fuck. They've had enough of my jokes too. Do I have a hydrogen bonded to nitrogen, oxygen, or fluorine yet in this drawing? I do have that oxygen to hydrogen, which sets me up with hydrogen bonding. That's going to be above my dipole-dipole, so I'd immediately eliminate that. So what we just processed through in 5 minutes took me a couple seconds, because I'm immediately deleting those things and ignoring them because they aren't relevant to what I'm trying to figure out. Okay, at least at a first pass, which is why solubility becomes tricky, and we'll deal with that in a second. Okay, which means the Cn, N being one of our very electronegative elements, is generating a polar covalent bond, because that doesn't fit in the nonpolar covalent or in the ionic, which therefore means I have a polar covalent bond, which then means dipole-dipole that is not hydrogen bonding. That should align to that force. Kind of, sort of? Okay, so that would be one that I would select. Is solubility more complex than that? Yeah. There's other factors that come into play. For instance, that has a long non-polar covalent bond structure, which means lots of LDF forces. Okay? Our polar aprotic solvents, that aprotic part, could very well include all of those London dispersion forces. Okay? So I would still select that as an answer choice. Okay? Moving through to the other ones. The ionic ones, I would not select at all. I'd completely remove those from play, because if I look at the ionic, that's a 2 jump, if you will, to get up to that force. So I would not select any of the ionic ones. What about the top choice? What did we say was happening in that top choice? Hydrogen bonding. Is hydrogen bonding that different from dipole-dipole? No. And so it sits right on that. Is that different enough? Is it not? How would you know? How do you know? It's a very unsatisfactory answer. You test it. You'd go into the lab and you'd test it. Okay? For the sake of this, I would click, or I would also, whoop, that's an eraser. I would also select it because it's in that system. So I'd have both of those selected as I ran through. Right? And if we submitted that, we'd probably be wrong because we're also only looking at part of the answer choices. Kind of, sort of? Okay? But that's the process that you should be approaching through all of these. If you're looking at your question 9 and you're like, I don't have that same question, you may very well not. But what you'll have is something that's asking about your solvents and solubility. Right? And because solubility is this nice, fun, tricky one, what we can go through and do is, as an added bonus, because Ivan was excited enough to ask me a question, we could potentially click that button. And if we go through and evaluate, what do we see within this? Selected. Selected. Not selected. Look at that. Almost like I was good enough to figure it out. Okay. What about the other ones? I would argue this one should be colored in blue, not just because it's not selected. Why should that one be colored in blue to match the other blue ones? It's ionic bonding. Okay. How did you say ionic bonding so fast? Because you did a pretty good job with that. You see the metal. I would argue you probably weren't thinking about the non-metal. You saw the metal, and as soon as you see the metal, ionic bonding. Both of those were ionic. That one's ionic, shouldn't be selected. So those all fit in the same category. What's going on with the other ones? What should you be zeroing in on when you focus on those? To me, I would color these different. Actually, I'll take that one. I'll take that one straight to red. Why should the red one be highlighted red almost instantly? Josie, did you say something? Yeah. Okay, again, the selective vision. I don't care about the carbons and hydrogens. Those are nonpolar covalent. Based off of the text that we had on there, we wanted dipole-dipole forces. Okay, so I don't care about the carbons and hydrogens. I don't care about ionic. What I care about is whatever's left over. Okay? I have a sulfur sitting in the middle of that. And if I'm used to reading my formulas quickly, I can find that sulfur and be like, that's not carbon or hydrogen, and it's not same to same. Therefore, it is a dipole or polar covalent bond connection, which then means dipole-dipole, which then means it matches my solvent, which then means I should be selecting that one. Whew. Good job. Okay. So what the hell's going on with the other one? Why would I, in particular, make that statement? How is that one different from all the others? It's the name of the compound, not the structures. Okay, and barely structures the other one. We're looking at formulas. Okay, are you required to be able to convert a name to a structure? Yes. Welcome to OChem. Okay, so you have to be able to go through and do that. Are you fluent enough to be able to do that conversion on your own? Like if I just said draw hexane to own, would you be able to do it? No, thank you. Okay, which means what should you do? Okay, look it up is sort of okay. What do you mean by look it up? Elaborate. What the own means, that's what I was looking for. Look at the nomenclature rules on how this translates out to a structure. Okay? If you've dealt with nomenclature a little bit, you should hopefully recognize that the most important part of that name, we'll change all our color patterns out, is right there at the end. The own. What does the own mean? Well, if I had all my functional groups memorized, maybe one of their names would set off alarm bells. I was like, oh, maybe that's what it means. Like aldehyde. What? A ketone, they have the exact same ending. That's where it's coming from. They're trying to align the naming. Okay? So we recognize that ketone's a functional group. Do you remember what structure it had? No? Okay, that's fine. Picking up pieces. So what you would then do is you now have a place to go. It's not just where do I see own in all of my literature. It's I want to look for a ketone. So we look up a ketone and we see that the ketone is, anybody know?
What?
What's a ketone?
It's the oxygen, the double bond to a carbon, and the carbon to other two carbons.
Ah, lovely answer all the way through. Oxygen double bond to a carbon is the most common response for ketone. It's technically wrong. This is a carbonyl. So what you elaborated on was that we have to note what that carbon is connected to. That carbon must be connected out to two other carbons. Because if it's connected out to an oxygen, it could be an ester or an acid. If it's connected out to a hydrogen, then it's an aldehyde. So we need that extra specificity to change it from carbon-oxygen double bond is a carbonyl. If I drop it next to carbons, now it's a ketone. Do I have the name converted into a structure yet? No. Do I care? Do I need to convert it all the way? You said no. Why? Okay. We have no OH. There's the potential that it could show up earlier in the name, but you're correct. Okay. There, hopefully what you would know is that if it showed up earlier in the name, we'd see a hydroxy. We're not seeing a hydroxy. So no OH. What else?
And the rest of it's just like carbons and then carbon and hydrogen.
So you're drawing out the rest of the structure. I don't want to draw out the rest of the structure. You're there. You're definitely there. I have every confidence that you have the answer. As soon as I've identified that functional group, I know I have that carbon to oxygen. That carbon to oxygen is a polar covalent bond. If it's a polar covalent bond, I have a dipole-dipole force. If I have a dipole-dipole force, that's similar to the dipole-dipole that we established from the polar aprotic solvent. Therefore, that one must be a correct answer as well. Ta-da! Make sense? Okay. Lots of individual steps and stages through it. Okay. Almost everything you have to do is an application of the rules all the way through. Smart Work will ask some gray area questions. I don't put gray area questions on the test. I put gray area questions in the homework to help you ask those questions so that we can have that conversation to ensure that you know exactly where you're supposed to be going. Make sense?
Yeah, so
Yes.
Is that, if anything that's ionic, is that polar or non-polar? Because I'm just a bit confused on like what's defines polar or non-polar.
What did I say about polar and nonpolar?
Well, like you were kind of like saying it really fast, so.
I said very aggressively something about the use of polar and nonpolar. Don't. Polar and nonpolar is not a classification you should be using. Okay? When we're talking about polar aprotic solvents, they're very particularly referring to a specific aspect, and we're talking about the bonds and the forces within those structures. Use that name to apply to the forces so that you can apply out to your structure. That's where it's coming from. By using the term polar, that can mean a lot of things. Water is polar. So is acetone. So is ethanol. So is octanol. Does that mean they all mix? No. Okay? So you have to be very careful with how you manipulate and use that term polar and nonpolar. Okay? Bare minimum, what it applies to is the bond connectivity. That's the only place it uses. If you're talking about solubility, do we care necessarily about the bonds? No, we care about the forces. Okay? So when we're looking at that term polar aprotic, what we're referencing is that it has polar covalent bonds. Well, what does that mean? That means it has dipole-dipole or hydrogen bonding. Look for the forces as your definition. Do not define any solvent as polar. Okay? Which is weird. That comes later. You got to run your forces first, then you can start applying the broader definitions. Does that make sense?
Yeah.
So a polar solvent is vague. That can be a lot of different things. Polar protic means something very particularly. Polar aprotic means something very particularly. It's not the single term on its own, it's in a group.
It's like you were saying, I think that OH was polar covalent? Or?
I said the OH was polar covalent. What does that mean about how it dissolves? A polar covalent bond gives me dipole-dipole forces. If I have dipole-dipole forces, I can now check for hydrogen bonding. Now I can compare that hydrogen bonding solvent to all of the forces for the other compound. I'm only using the bond to allow me to find the forces. Once I know the forces, now I can make a comparison. Kinda? If you're referencing the OH here, this is a slightly different scenario because we're actually not. In fact, I didn't reference the OH here. What did we reference here? The metal. That was the focus here. So when we're talking about OH from this, all I care about is that that's a metal, which therefore means it's ionic. I don't care what's happening out there. I'm already in my force category. Okay? Why does this top one become a tricky one? What force did it have? Ionic. Where's the metal?
There's no metal.
There is no metal, so how would you know that that was ionic? That's content you've seen for at least 2 semesters that you should theoretically know already. Okay? And if you don't know that, that's where you ask. Okay? Even on a test, you're like, I don't know what this symbol means, what this is supposed to be. Okay? And you now have to leave it to me to decide, is that something that I think you should know from this class, or is that a prior knowledge thing? And if it's a prior knowledge thing, it comes down to a coin toss on me telling the whole class. Homework, you should be looking for that prior knowledge. Okay? Does it make you more satisfied or less? More? Okay. What I'm effectively having you guys look at when we talk through this, and I'm going to start this because, see, this is why I put notes on slides, is what I'm showing within this kind of color wheel. Some people like it, some people don't, but ultimately this is what we're referencing. A polar covalent bond generates dipole-dipole forces. Okay? The forces are what's dictating our physical observables. That's melting point, that's boiling point, that's solubility. That even moves into reactivity is all dealing with the forces. Those forces are ultimately derived back from those bond definitions, which is why you need to be able to look at a structure and identify those bond definitions so that you can qualify the forces, so that you can qualify all the different properties that come out of it. Okay? Why pull this back up? This thing on hydrogen bonding. Okay? Hydrogen bonding is an interesting one. Let's not do that one. That green dotted line, dashed line, what we're trying to represent is the force between the nitrogen and the hydrogen, not away or towards bond. What force is that? It's hydrogen bonding. How do we figure that out? Well, the first thing we do would be look at the first bond, okay, the hydrogen as part of that interaction. That bond is a polar covalent bond, which when it goes out into the world would generate a dipole-dipole force because this single thing is a dipole. If I go over and look at the other side, what kind of bond do I have between the nitrogen and the carbon? A polar covalent force or polar covalent bond. Why is it polar covalent? Is it ionic? Do you see a metal? No. Do you see same atom to same atom? No. Is it carbon to hydrogen? No. So it's not ionic and it's not nonpolar covalent, which therefore means it's polar covalent. What kind of force does that generate? A dipole. Okay? And officially dipole-dipole is when it interacts with something else. Why do we call it that? Well, if I take this dipole that has a negative and a positive, and I align it with this dipole that has a negative and a positive, what is the forming interaction between those two dipoles? Dipole-dipole. That's where the name comes from. Okay? It's referencing what happens when I bring those two things near each other. So that is absolutely a dipole-dipole force. Okay, but two people answered my question, what's the force here? And both those people unanimously said it was not dipole-dipole. Or they didn't say dipole-dipole. They didn't say not. Okay? Slightly different meanings. What they said, it was a hydrogen bonding. Once you've established that you have a dipole-dipole interaction, you now have to ask, do I have a hydrogen that is physically bonded to nitrogen, oxygen, or fluorine? So I go back up to my system and say, there's my hydrogen. Is it physically bonded to, solid line, nitrogen, oxygen, or fluorine? If the answer to that is yes, that dipole-dipole force carries on new meaning, and that's where we shift to hydrogen bonding. Kind of, sort of? Typically, when we talk about solubility, we're looking, or not solubility, just an individual substance and its force, we're looking at it in a like environment. So we can look at water and say water is a hydrogen bonding solvent. All we're looking at is the formula of water, but what we've done is extrapolated however other many amounts of water molecules we want around it to say the interaction between those is hydrogen bonding. Okay? In that scenario, there's no need to define the hydrogen bonding interaction further. But if we move to this scenario, we want to define it just a little bit more because each of these molecules is interacting differently in the formation of that hydrogen bond. Okay? The water molecule, the one on the left, is the one supplying a positive hydrogen. So the one on the left we would call a hydrogen bonding donor, because it's supplying the protic hydrogen. The one on the right is a hydrogen bonding acceptor, because it is the one accepting the hydrogen. So if we're now to look at an individual structure and we want to identify wherever hydrogen bonding can happen, where can hydrogen bonding happen? It can happen at both an acceptor and a donor. Does the acceptor have to have a hydrogen? No. What does it need to have?
Nitrogen, oxygen, or the other one?
That's fair. Nitrogen, oxygen, or fluorine. Okay, and all we really care about is nitrogen, oxygen. Fluorine just probably won't show up. Okay, so nitrogen and oxygen are hydrogen bonding molecules or atoms because they can act as acceptors. It doesn't matter what they're bonded to. They're electronegative enough that they will always generate that partial negative, which allows them to act as hydrogen bond acceptors. What about the flip side? Hydrogen bonding donor. What do I need to see?
Hydrogen.
A hydrogen. I love that answer. Thank you. I may have cut you off, but that's appropriate. I needed to cut you off. Do I still have that hydrogen?
No, yes, but not that.
I absolutely still have that hydrogen, which is why I wanted that answer. So thank you for that. Okay? The hydrogen bonding donor isn't just the presence of a hydrogen. That hydrogen must very specifically be in a polar covalent bond and must very specifically be in a polar covalent bond where it is bonded to nitrogen, oxygen, or fluorine. Is it bonded to nitrogen, oxygen, or fluorine in this scenario? Which means, is that a polar covalent bond? No. That's now non-polar covalent. That word. Sequence of words. And if it's a non-polar covalent bond, what's the force? London dispersion. What's the force now between these two molecules? I'll kind of accept that. It's this weird gray area. Officially, it's LDF dipole. Okay, we typically don't reference that because it's an ugly name. But it's not dipole-dipole anymore, which means hydrogen bonding is now off the table. Kind of, sort of? So our donor, our hydrogen bonding donor, is a hydrogen, but it must also very specifically be connected to oxygen, nitrogen, or fluorine. And if it is not connected to those, it can't contribute to hydrogen bonding. Kind of, sort of? Does that answer your question, Isabel? Maybe? Okay. I may have already answered it in email, but that's where that's coming from. We good? Close that. Come on. Do what I want. Kind of leaves me stuck at looking at Newman and chirality. I was kind of hoping we had other questions. Do we have other questions, or is that really what we're digging into? Maybe a couple of other questions. What do we got?
Yeah, I wanted to go over Newman.
Okay.
Sure.
You too? Okay. Okay.
Great on this one.
Newman I'm okay with, believe it or not. Chirality I don't like. It makes sense to me, but that's after like 20 years of working on it. So let's take a look at Newman. What have we drawn?
C something.
Let's go to the formula. So you could just say C2H6. I'll give you that. Okay. CH3. What else have we drawn? So this is an odd question. What I'm asking you is, what do you see? Okay. Good reference on the F. It's not ethyl, because ethyl would mean it's a substituent. So we could say it's ethane. Good. So we're pulling in all this content that you've already seen. Anything else?
Non-polar covalent.
Non-polar covalent bonds. Cool. What else do you see? kind of as we push on this, because I'm starting to see some people write down, I'm not sure I would write any of this down. This is you trying to dredge up the information that we've already talked about in the class and try and remember what things you're responsible for knowing and seeing in this. We could look at sp3 hybridizations. I heard London dispersion forces. Sigma bonds. Tetrahedral. You see tetrahedral. Why not really?
They're drawing the same plane.
We pull out our hands and summon the devil. Yeah. Okay. Tetrahedral. Good reference. I love the reference. I don't really see tetrahedral because to see tetrahedral, I need a three-dimensional system. What I would argue that we've drawn here is a Lewis structure. Lewis structures are great at showing our connectivity, and we could make lots of conclusions about all those other things that you've already done. That's fantastic. But what it doesn't do is accurately represent the three-dimensional molecule. To see the three-dimensional molecule, we'd now need to bring in that three-dimensionality. That's where we need wedges and dashes. So we could go through and now add that information. I could put a wedge there. I could put a dash there. Okay? That side doesn't matter. What about the right side? So we've now pinned one side down and said this is where it's at. Where should I put the wedges and dashes on the other side? Does that matter?
Yes.
Ooh. If you're already saying yes, why do you need me to talk about Newman? It sounds like you already know it.
Because I don't know why it's yes.
Okay, that's fair. Yes, it's important, but I don't know why. Okay, well, if we don't know why, what should we do? Google's not going to help you. Right? You said it's important to define our wedges and dashes on that side. That we can't just drop them willy-nilly on it. And if you don't know why, what should we do?
Ask you.
Not horrible, but I've asked you first. Try to find out why. So what would you need to do to try and find out why? I love it, yeah.
I don't know. I guess use every material that I have, which is maybe the model kit, maybe look at.
So looking at a model kit is eventually where we'll go with it, but right now we don't have a model kit. This is drawing it. Why does it matter to draw it? If you don't know why, guess, draw. Draw something and see if it matters. Okay? So what I'm going to go through and do is I'm going to draw it like this. And like that. Okay? On the other side, I'm going to take a guess and say, well, maybe it should have been like this. Come on.
Would it have something to do with antibonding?
No. Thankfully, we can ignore molecular orbitals for the most. Does it matter? So now we run into the interesting dilemma, well, I still don't see this, Mike. I need help visualizing this. This is where you could bust out the model kit. Okay? And arguably, we could look at this and say, well, I don't see any difference. I don't think there is one. Okay? And that's when some smart aleck comes in and says, well, yes, there is one, because you're looking at this from the wrong direction. You can't see it. So you need to change your viewpoint on the molecule to understand what's going on with it. Because we went through and said it was irrelevant and not important, the person that then went through and said we are wrong then gets to name it. That's how it works. Okay, we accept it's not important until somebody says otherwise, and then we give them credit where credit is due, that they found that it was important. Okay? And so what they went through and did is said looking at it from the side was not useful. What you needed to do was turn and look the other direction. Okay? I'm trying to come up with analogies and I can't think of anything in my head. Okay? Like looking at someone from the front view versus the side view changes what you could potentially see or visualize out of them. Okay? Looking at me from the front, maybe you can't tell if I have a belly or not, but if I turned, then maybe it changes.
Yeah.
Okay? Same kind of thing is happening here. Kinda? Does that kind of make sense?
Starting to.
Okay? So what we're trying to do is just say, well, how else can I look at this molecule? Okay? And so what happened, and this is where we now go through and say, There's my eye, my sketchy eye. I'm going to look at it from the side. So this molecule is effectively like this, right here, with the iPad. What I now want to do is turn and look at it from the side. What happens or what changes with my viewpoint within that system? Okay? So what we've got to do is decide where we're looking from and all that fun jazz, and then make those actions. I've drawn the eyeball so that we know what's in front. Okay? This carbon, let's not make it red, that carbon is then going to be in front. Right? So I could draw that carbon. Okay? How about the top hydrogen?
Straight up.
Straight up. How about the wedged hydrogen?
Be to the right.
It should be to the right, thank you. Okay, to the right and a little bit down. I shouldn't be drawing it up here, I should be drawing it down. What kind of angle am I trying to show in here? That becomes a little bit challenging to see. It's not 109.5 because it's three-dimensional. Technically what we're seeing there is 120 within that, because it's just 3 bonds that we're seeing. Okay, so this was the former, we'll call that wedge, W for wedge. And the other hydrogen that was dashed is now towards our left, also equally down, and that was dashed. So far, so good? We're about to make it real messy. Back carbon will keep black. Okay? If we look where my eye is supposed to be, it's supposed to be in perfect alignment with the bond between the carbon and the carbon. Which means, can I see the bond? No, the carbon atom's in the way. Which also means, can I see the back carbon? No, because the front carbon's in the way. Okay? So if we're going to draw this in a three-dimensional reality, that back carbon being further away, I should draw kind of smaller. So we'll draw that inside there. Right? Three-dimensional, things further away. Okay? Where's that top hydrogen?
Behind the hydrogen, or behind the first hydrogen.
Straight up, which happens to perfectly overlap with the other one. Okay? Where's the wedged hydrogen?
Same place as the first wedge.
Dashed. Same place as the dash, right? Okay, and if you're looking at that and being like, that's really ugly, it is really ugly, so we make adjustments to this so that we can theoretically see it a little bit cleaner. First adjustment that we're going to go through and make is reverse perspective. I need to be able to see the back atom. So what I'm going to do is define the back atom as a circle. That's a circle, trust me. Okay, and it is bonded to 3 hydrogens. There's the one straight up. There's the hydrogen that was wedged. There's the hydrogen that was dashed. That front carbon, I don't want to block the view of my back carbon. So the front carbon I'm going to define as a point. Okay? That point is exactly in the middle. Okay? I still have the hydrogen connected to it. And as we look at that, you might know, it looks like you twisted a little bit, Mike. Why would I twist it? So I can see it. It's just visually easier for me to see it instead of drawing everything directly on top of each other. That's what we're doing. That's it. Okay? That viewpoint on the molecule now, because someone went through and said it's important. We haven't even addressed why it's important. Okay? But we're saying it's important. That viewpoint is now known as a Newman projection. You are sighting down one bond, which becomes one of the other tricky things. Is it possible a molecule could be rearranged in such a way that you could sight down 2 bonds simultaneously? Yes, we will do that later in this unit. Okay? Yes?
They referenced gosh, or how you...
Yeah, we'll get to that.
Oh, okay.
Okay? Can't actually see that with this structure. Well, we still haven't said why it's important, so let's look at the red one. We said we couldn't see it in the red, so we'll do the same process. Okay? We're going to keep the eye in the same space, so that back carbon I'm going to make black. This time I'm not going to go through the messy middle work. I'm going to go straight to the pretty Newman. We okay with that? Cool. I'm going to accept that as an answer. That back carbon, big circle. Why am I going to pick the hydrogen aim down to draw first? Say it again. I'm not. You're not wrong, but it's not quite clear enough for me. What are you saying? It's in the same plane of the drawing. Okay, so that plane of the paper, okay, the iPad, it's in that same plane. So if I twist, it's still in that same plane. Okay, straight up and down. So it makes it a little bit easier for me to deal with. It's just my plane of paper is switched. The wedges and the dashes were not in the plane of the paper initially, and now I'm twisting them are still not in the same plane. So they're not easy to draw. I have to think about them a little bit more. Does that make sense? So I will always tackle the solid lines first. Wedged hydrogen. Where should it be drawn?
To the left. Well, for you, yeah.
Do it for you. Don't do it for me. It's just going to break me all the harder.
Top left, like diagonally.
Okay, so we're hearing top left, so I'm hearing over here. Does everybody agree that's where it belongs? Okay, no, we got an immediate no.
To the right.
Okay, it should be to the right. We're looking at the molecule coming in this direction. Where's that wedge? There's my thumb.
Forward to us.
If we're looking at it this way at it, which side is it on?
Right.
It's on the right. Okay, and this can be some of the confusion because you're like, oh, I'm going to change it so Mike can draw it. Don't do that. It's not going to make it easier for me to draw. Okay, it's just going to add more confusion behind it, which you may or may not be doing. Okay, so that should be on the right. This was, what do we say, wedge?
Yeah.
Where's the other hydrogen? That's now on the left, and that's our dash. Okay, because that was going behind the plane. Does that make sense? Okay. Front carbon. Red dot, right in the middle. Which hydrogen am I going to draw first?
The top one.
The top one. Why the top one? In the same plane. So I'm picking that solid line again. Where is that going to go?
Straight up.
Straight up. I think we're getting it, so I'm just cheating and drawing all that in. We okay?
Yeah.
Is there now a difference?
Yes.
Ooh. Okay. So Newman went through and said, well, if I look at it from this angle, now I see this difference that was not clear when we looked at it from the side. Okay. Once you understand that, you can actually see it from the side. You just have to acknowledge that extra piece. It's a little bit harder to do, but you can do it. Newman acknowledges that the arrangement of those atoms, or those bonds, are different. Because they're different, what does he want to do? Name them. Okay? So now we go through and name those particular interactions. Well, what do you see? Or not see? I don't see these things because these things are overlapping with each other, right? Kind of like when the moon passes in front of the sun.
Eclipsed.
We get an eclipse. Whereas over here, they're like alternating around, right? We might call them staggered. I don't know how to spell staggered. Close enough. Right? That's Newman. That's it. That's all Newman is. Acknowledging that there's a difference between these. Okay? How does that difference manifest? Okay, so when we're talking about those differences kind of manifesting, really what we're asking is what is the difference in energy between those two things? Okay, and if we're saying they're different, that means there must be some energy difference. Would I expect one of these to be more or less stable than the other? Yes. Why and which one? What do you see?
I think staggered is more.
More what? More energy, more stable?
More stable.
More stable, okay.
Because, like, all of the compounds are, like, far away from each other. Like,
I don't like compounds.
like the,
Electrons.
for example, yeah.
In particular, what electrons are away from each other? The hydrogens are further away from each other, but I would argue there's a more relevant one to look at. What does that line represent? A bond, and a bond is electrons. So it's staggering the bonds away from each other. That would mean the staggered conformation would be lower in energy because the electrons are not occupying the same space. None of them are technically occupying the same space. They're occupying the same plane if we were looking at the eclipsed. They don't like that. That's an electron repulsion. So what happens? That hydrogen in front, let's leave the back one static, the hydrogen in front goes, I don't like being here, and so turns. How can it turn? What's connecting those two carbons is a sigma bond, and the sigma bond can freely rotate. So it's that free rotation that's alleviating that stress of the electrons overlapping. Okay? And so what it does is it turns into the staggered system. Okay? Could the bond still rotate? Yeah, absolutely. But as it rotates off the staggered, what happens to the energy? It goes up. And then it's eclipsed. And then what happens to the energy? It goes down because it starts to become another staggered conformation. Everybody see that?
Yeah.
Okay? So you will also see sometimes referencing graphs. And it goes, oh, I don't understand the graph. Do a rotation. What happens to the energy? Well, the bond starts to overlap more, which means the energy goes up. Then it goes down. Then it goes up. Then it goes down. And you see these hilly diagrams. That's all they're trying to say is the energy is changing for each of those. That's it. We will not quantify them. Leave that to somebody else to quantify. I don't want to deal with it. Yes, Jess.
So the staggered is lower energy but more stable.
And this does become one of the confusions. Okay, we get opposites all the time. Stability is always in reference to lower energy. So low energy is more stable. So we get those opposite terms popping up. You got to be careful with it. And I'll misspeak them too. So feel free to call me out on it. Okay? This was a relatively simple molecule. What happens if we make it more complicated? Okay, so the next kind of step up is instead of it being ethane, I add 2 carbons. How does that change the overall system? Okay, well, the first one is still eclipsed. Where are my CH3s?
All on top.
I drew them on top. They have to be on top. So let's backtrack out of that. Let's see if I can do that carefully. I'm going to regret it, but I'm going to do it anyway. Oh well. I can't see anything. Okay, I shouldn't have backed out of it. Don't laugh at me, it's mean. CH3. What happens now? Are they on opposite sides? CH3 I drew in is on the wedge. Are they on opposite sides? No, they're not straight up anymore. They're now both to the right-hand side. Okay? That interaction is identical to the one I drew before, which becomes one of the confusions. Everyone goes, oh, they're not straight up and down overlapping, so it must be something different. It's the same interaction, except what did you do? You just turned the molecule. Okay? That doesn't change any of the overall energetics. It just literally just rotated it. Okay? It's still the same interaction that we're picking up out of it. It is still going to be eclipsed. Okay? What happens with the other one? Oh, yeah, that's right. I deleted all those. I find it vastly easier to do all the manipulations on the solid lines, okay? Which is why you typically see it on the straight up-downs, because it's easier to draw those. But that's it. It's an artifact of your instructor, not a reality. Kind of make sense?
Yeah.
So we go over to here, and I draw in my CH3s. These are going to be on that straight up-down, but they could have just as easily been on the diagonals. And now that I've drawn it, I can make it to the diagonal. Should I make it to the diagonal so you see what's going on? Yeah. Back in that. Different way. It's always more than one way, right? Hydrogen. Erase that, erase that. Hydrogen, hydrogen. I still want the staggered for these CH3s. Okay, what if I put CH3 on the wedge on the front carbon. Where should that CH3 appear in my Newman?
Bottom right.
Bottom right, awesome. Okay. Where do I want to place the CH3 on that back carbon? Not you, Adolfo, right now, because I think you've got this down pretty well. Okay, you can keep it in your head, but don't answer it out loud. That CH3, I'm drawing it right there. Needs to be black. Where do I draw it on my black carbon? There's 3 slots. CH3 needs to be on the dash there. So they're going opposite directions. Everybody see that? Okay. If we go through and run this manipulation now, we should hopefully see that we're still eclipsed, we're still staggered. Okay, and everything's fine and dandy and happy, and we can all go home and say, well, nothing new happened, so we don't need to worry about it. Except, of course, that's a carbon-carbon bond, and the carbon-carbon bond can freely rotate. What happens if I freely rotate? So, way out of space here. Can I delete all the stuff up top? Okay. I'm going to rotate this one. Okay. We'll leave the back carbon alone. So back carbon locked in place. Call out that orange. Okay, and I'm going to rotate, grabbing that CH3, and I'm going to rotate it clockwise. Okay, so as I rotate it down, what happens to the energy?
It goes up, so it goes down.
It goes down. Okay, I'm going to keep rotating, keep rotating, keep rotating. What happens to the energy?
Up again.
Comes back up. That's where I want it. I want that CH3 overlapping my black HD. Okay, that's what I want to draw. Okay, so in that scenario, there's my CH3, there's my H, there's my H. Everybody okay with that? Easy peasy. Okay, if it was easy, why'd you ask about it?
Because I didn't know.
Okay. Is that an eclipsed interaction?
Uh,
What was eclipsed?
Same atom over the same atom.
This comes down to now defining what that interaction meant. Okay? It didn't necessarily mean same atom over same atom. What did we specifically reference? That the bonds overlapped. When we add in a new atom, that does add another layer of kind of confusion behind this. And if we now go through and look, these probably do not have the same energy. Why not? Still the bonds overlapping. Why would they be different energies?
Something about that CH3.
What's different about the CH3 from where we looked at it before? What was it before? What were they before? What'd you say? No, because it wasn't, you're still referencing CH3. Before we used CH3s, what was it? Hydrogen. What have we changed? We've made it CH3. So yes, it has to do with the CH3. What's the difference between CH3 and hydrogen? Okay, what is it? How is carbon different from hydrogen? The electronegativity difference is next to nothing.
Different elements.
How is it a different element?
There's more elements now, isn't there?
I don't know what that means.
Valence electrons?
What was that? It has more electrons. What we were talking about in all of this is electron repulsion. So as soon as I drop in a CH3 here, that has more electrons. That's going to change the energetics. If I have another CH3 in the back, that also has more electrons, which means I put the two electron-heavy groups right next to each other. That's bad. If I do the rotation up, still eclipsed, but now my electron-heavy groups are next to hydrogen, which has less electrons. So should they be different energies? Yes. And if they're different energies, what should we do?
The lower energy.
We should name them. Okay? I would argue are relevant for these two. I don't want to bother to name either of those. Okay? And the reason for it comes back to the diagram that we could draw for this as we did a rotation. Okay? Let's see if I can pull this off. So this is rotation. We'll call this bottom, and we'll call that one the top. Okay? If we look at the bottom, high energy or low energy, where we start? High. So I'm going to start up here. Okay, what happens as I rotate this down to get it to look like that one? What happens to my energy? Energy starts to go down. Then what happens? It has to go back up. Does it go back up to the same height? No. So it goes up to a slightly different height. So theoretically, we can see that those are different from each other, right? Why do I not care about those points? Imagine it like a roller coaster. Okay. Where are you at when you finish the roller coaster? Yes, where you started. Are you at the top or the bottom?
Bottom.
You're at the bottom. Why?
Over.
It's lowest energy. What happens when you get up to the top? It's the highest energy, and what do when you hit that highest energy? You fall down to get back to the lowest energy. So when we're talking about these systems, this is a high energy state for the molecule. I can't get to that easily because what is it going to immediately do? Rotate away. And if it immediately rotates off axis, is it ever really existing at the peak? No. So why do I want to name it? It's not something that's going to be energetically useful for me to look at because it's never really existing at that state. It's existing at the valleys, not the peaks. Okay? So to me, I don't think it's relevant to name the difference between those. They're both eclipsed. Okay? And the general rule from what I've seen ACS output, they don't care about the naming of both of those either. Okay? And I would argue when we do a similar thing over here, they kind of don't care about the naming behind them either. Okay? The big deal that comes out is, do you understand the difference in energy behind those? Yes? Great. That's the important message. Knowing that it is eclipsed or staggered isn't really relevant. But if we have the name to attach on it, we have something that we can potentially memorize and make our life a little bit easier. Kind of, sort of? Okay. What happens with the staggered?
Low energy right now.
It's low energy right now. So what we're going to do is we're going to grab, I said we locked the black one, right? The black one, so there's, oof, that was a horrible circle. I don't see you drawing one. Okay. And we're going to take this CH3, and as we rotate it again clockwise, that front one, it's going to go up, and then it's going to go down, right? Okay. So if I do that drawing, we should get the CH3 over here. Okay. That whole OH conversation we had a little while back, note what happens when I draw my CH3. I'm dropping the hydrogens on the outside, so I'm showing the bond connectivity a little bit better. Yeah. Subtle change, not a big deal, but subtle change in how our formula is written out. Okay? Staggered or eclipsed? Staggered. The bonds don't overlap. Absolutely, it should be lower in energy than both of these ones in our eclipse scenario. Compare it to the very first one.
Huh?
Top to bottom. Are they the same energies?
No, I feel like the top one has more energy.
Why is the top one more energy?
Because that CH3 are closer to each other, so the electrons are
Yeah, I love how you took that all the way through. The CH3s are closer to each other, which means the electrons are closer to each other, which means that structure is higher in energy than the bottom structure. Okay? Is this an energy minimum? As I rotate that CH3 counterclockwise, what happens to the energy? So I take that CH3 and I pull it down this direction, what happens? It goes up. What happens if I take that CH3 and I push the other direction? It goes up again, which means is that top drawing a minimum? If the energy goes up when I turn one way and it goes up when I go the other way, am I existing in a minimum?
Oh, yeah.
Yeah, I'm existing in that valley, right? Okay, and as we just discussed over here, we don't care about those because those are peaks. This is a valley. This is a valley. Because of that, I now do want to distinguish those and name them slightly differently because those energetics are now important to me and I might go through the process of naming. Which gets us to the nasty words of gauche and anti. Gauche being above and anti being below. Anti might be helpful because they're on anti sides. Does that make sense? Like they're on opposite sides. So you take your largest groups and are they completely opposite each other? Yes, there's anti. Okay, that's where that name is referencing. What's happening with gauche? Gauche means awkward. So if you watched the video, you probably heard the urinal explanation, right? Which I think is actually a pretty funny, right? It was a decent explanation if you know anything about urinals. Okay? Gauche is awkward. You're bringing the two things too close to each other. That's not a particularly energy minimum. Okay? Both guys are now clenching a little bit, like, why are you just standing close to me? Okay? Because there's not another urinal. Okay? So that's a little bit higher energy state than this one. But we're not pissing in the same urinal. Or other things in the same urinal. That's also equally bad idea. Okay? And that, I think this works for women too, right? I mean, do you use the same toilet that somebody else is using while they're using it? Like, that's a little, not quite, but you might go next door. Kind of, sort of?
Yeah.
Okay. I don't know about female bathroom etiquette, sorry. Okay. But that's what's happening within Newman. It's just, hey, we shift off. Why do we shift off? Do we see these different energetics? Why are those different energetics important to us? Spin this all the way back out, and if we were to draw out the Lewis structure for butane, trying to represent its three-dimensional character best, what you would probably see, or really any carbon chain, is you see the zigzag. Why are you drawing it zigzagged? Why aren't you drawing it?
Hydrogens and electrons repelling each other.
These bonds are in the same plane, and I want those electrons as far away from each other as possible. You mean the anti-configuration? Yeah. And if we look at the other drawing I've got, I'm placing those electrons now in the same space. That's a higher energy state. So we tend to draw our drawings in this extended zigzag structure because of Newman projections. It's a lower energy conformation. Okay? With that, I apologize. I did want to talk a little bit about chirality, but we've got, today's Tuesday, right? Yeah, we got Thursday. We can destroy everybody's hopes and dreams with. Okay. With that, we are done. If you've got lab